Hello everyone and welcome to another lecture. In this lecture we are going to see some features of the determinant. So let's say I have a matrix called A and I have a matrix called B. So if I multiply them using the standard matrix multiplication, then the determinant of AB combined will decompose into determinant of A and determinant of B. That is this property over here. Now, for example, let's take A equals to 1 0 0 1, which is the 2 cross 2 identity matrix, and you can compute the determinant and it turns out to be 1. And let's take B to be this matrix 2 3 0 1, and this determinant is just 2. Now if you combine them, you can see that AB is just 2 3 0 1 and the determinant of AB is 2 minus 0, that is just 2. And if you see on the right hand side on this part, again we are getting 2. So this is a property of determinant, that it's acting like a multiplicative operator. So let's say instead of two matrices, let's say I have the most general case, that is I have A1 A2 AN, and all of these are square matrices of the same order, and I want to compute their determinant. So this will decompose into determinant of A, determinant of B, oh sorry, not B, so this will decompose into determinant of A1, determinant of A2, determinant of AN. This determinant is a non-linear operator. What do we mean by a non-linear operator? Let's say you have a matrix called A and another matrix called B, and you have A plus B, another matrix, right? Now determinant of A plus B will not be equals to determinant of A plus determinant of B. This is what we mean by non-linear, that is, it is not behaving as a linear operator. Recall that any linear operator will satisfy this. Let's say I have a linear operator L and it is acting on, let's say, matrices A and B again, so this will be true. So this is the condition for a linear operator, but determinant doesn't satisfy this, so we call determinant a non-linear operator. So let's now check another case, and let's take a scalar that K belongs to the complex number and A is some matrix, and we want to evaluate what is the determinant of K A. So the first thing that might come to your mind, that maybe this is just determinant of A, which is a number, times K, right? This is the thing might come to your mind, but as we will see, this is not the case. Not the case. Why? Let's try to clarify ourselves using an example. Let's take the identity matrix I, the 2 cross 2 version, and let's take K equals to 5. So 5i is just 5005, right? And if you compute the determinant of 5i, this is 25, but the determinant of I is just 1. And if we had this over here to be true, that is K times determinant of A, we would have written 5 dot determinant of I, right? But as you can see, these two are not the same. so please be careful about it. In this case, we have to actually evaluate what the matrix phi by is, and then we have to compute the determinant. Now I would like to finish off by trying to motivate a physical interpretation of determinant. To do that, let's start working in a Cartesian coordinate system that is denoted by x, y, and z. And let's say you have a small cube over here like this, and you have sides with, let's say, dx, dy, and dz. The infinitesimal volume in the Cartesian coordinate is denoted by dx, dy, and dz, right? Now what if I use coordinate transformation, that is ordinate transform, and I move to the spherical polar coordinate. Let's do it with the blue color. So this is my sphere, and we will denote our Cartesian coordinates with the dotted lines in this background. So that we can relate these two pictures. And in the sphere, that is in the spherical polar coordinate, we have a r direction that points radial outside, the theta direction that makes an angle theta between the r and the z, and a phi direction like this. So if we look at this cube in this coordinate, it will look something like this. Let's draw this with another color. Where it will have sides with d